Hello and welcome to the first video of section 1.6 on limit laws. In this video, we will discuss the fundamental limit laws, which will aid in calculating limits. In section 1.5, we use the graph of a function to obtain an intuitive understanding of limits. We visualize the limit at a point as the height of two ants crawling from left and right when and if they meet. This section will move beyond a graphical understanding of limits to an algebraic one. How can we calculate the limit as x approaches 1 of the function f without graphing the function? Can we just plug in 1? Not really. The actual value of f at x equals 1 is not necessarily the same as the limit as x approaches 1. Our informal and graphical understanding is not sufficient or rigorous enough to calculate the limit. To be honest, we are not going to be treating limits in a truly mathematically proper way. If we were doing things rigorously, we would start with the formal definition of a limit and use it to carefully develop further techniques. If you would like, you can read more about the formal definition in section 1.7, and if you take mathematical analysis, you will properly learn limits. The problem is, this type of rigorous approach requires a lot of mathematical training. Instead, we will focus on intuition and tools necessary for Calculus 1. The following limit laws are derived directly from the formal definition of a limit. As we learn these laws, keep in mind, they only hold when the premise holds. That is, they are only guaranteed to hold when the limit of both f and g exist as x approaches a. The constant limit law states the obvious. If a function outputs the same value, say 5, for any input, then the ants crawl only at the height 5. So the limit, the trend, is 5. The identity law has similar reasoning. If y and x are always the same, then y approaches a whenever x approaches a. If the limit of f exists, then the constant multiple law says that a constant can be multiplied before or after the limit is taken. Since we know the limit of x exists and is 3 whenever x approaches 3, the constant multiple law gives the limit of 4x to be 12. If the limit of both f and g exists, then the sum and difference law states that the sum or difference of the functions can be taken before or after the limit is taken. In these cases, the order of operations is not fixed. Since we know the limits of x and 7 exists, x plus 7 approaches 9 as x approaches 2. Similar to the previous laws, the product law states that the product of two functions can be taken before or after the limit, provided that the limits of each function exists. Since we know the limit of x exists as it approaches any value a, the product law can be used to show that the limit of x squared is a squared, the limit of x cubed is a cubed, the limit of x to the fourth is a to the fourth, as both the limits of x and x cubed exist. The pattern holds true. The limit as x approaches a for x to the n is a to the n. This continues to hold true for general functions. If the limit of f exists, then the function can be multiplied to itself n times, or have the limit taken in any order. We can tweak this pattern slightly. Instead of taking powers, we can take roots before or after the limit, provided that the limit of x exists. This is a fact that is provable once we discuss continuity later in the chapter. Our final law, the quotient law, says that a quotient could be taken before or after a limit, provided that the limit in the denominator is non-zero. Can you think of a reason why we need this condition? Well, without it, we would be dividing by 0. Let's conclude with an example. Is the denominator's limit 0? Well, let's calculate it. We know that the limit of x squared, 5, and 1 exists from the constant and identity laws. So we can use the difference and product law to bring the limit to both terms of the difference and inside the radical. We find that the limit of the denominator is 1, not 0, so we can use the quotient law. The limit of the numerator exists by the identity, constant, sum, and product laws. So the limit of the numerator exists, as well as the denominator. The quotient law holds, so we can bring the limit to the numerator and denominator, calculating the limit as 12. You've seen the basics. Now work towards mastery through practice and study.